should be okay now, yeah. So it's my pleasure to welcome today Laura Pentericci from the Observatory of Rome. Laura did her PhD at Leiden in 1999, and then she moved for 4 years to the MPIA at Heidelberg as a research fellow. And then she moved back to Italy to get a permanent position at the Observatory of Rome. She's now also one of the ANA editor for the cosmology section. She's a well-known expert on the formation of the first galaxies, and today she's going to talk on unveiling the high redshift universe, a view from deep optical spectroscopy. Laura, the floor is yours.
Thank you. So thanks, Nicholas, for the invitation, and it's a pleasure to be, well, with you, only if just virtually. So I hope to visit soon as it's possible. It was also actually very enjoyable to have this talk with the students before. So I will talk today about the results we're getting from this, the VANDELS survey, the spectroscopic survey of which I'm PI, and how in general we can probe the high redshift universe with deep optical spectroscopy. We can say that in the last few years, the progress in understanding galaxy evolution at high redshift has been considerable, has not limited anymore by poor statistics. We now know many galaxies that are redshift. We have identified many of them. But so the progress is actually limited rather by the systematic uncertainties in the way we can measure some crucial physical parameters, such as, for example, age, dust attenuation, and metallicity, and parameters that are have the genders which are interrelated. And I will try to show how systematic spectroscopic follow-up is needed as a key complement to deep multi-wavelength data to make further progress in this. So as I say, a lot of what we know now about high redshift galaxies, and is now really a lot, comes from the deep observation mainly with HST of small regions in the sky. This is a nice figure I stole from Carl Illingworth, and shows some of the deepest fields that have been observed with HST, so namely the CANDELS field, but also the frontier fields. And from these tiny regions, we have been able to identify many distant galaxies up to redshift 10. And so thanks to these deep observations with HST complemented by Spitzer IRAC data, I also have the pointer here, we have been able to identify galaxies which are, for example, detected in the near infrared and are not detected in the optical. And by determining their photometric redshift, we know that they are really most probably very distant galaxies. And these are, for example, some of the recent results at redshift 9 in this, some of the CANDELS field by Bowers and collaborator, redshift 9 galaxies. So with this wealth of data, we can, for example, study how the galaxies as an ensemble evolve. For example, we can determine the luminosity function, which is essentially census of galaxies, how many there are and how luminous they are. And luminosity function and its evolution are key parameters to understand how galaxies have built up. For example, these are the determination of luminosity functions from redshift 4 to 8, done with more than 10,000 galaxies selected from all the HST deep and wide field by Bowens and collaborator. And here is the extension of the luminosity function up to redshift 10, which has been obtained thanks to the inclusion of the lens field. So with lensing, we can probe the faint end of the luminosity function. And for example, here we can see the evolution up to redshift 10. And as a complement to this very deep observation and to the lensing fields, we also have the large area ground-based surveys, which probe the bright end. So they can constrain the bright end of the luminosity functions because, of course, to be able to find these bright but rarer objects, you need large area surveys. So for example, these are data coming from Cosmos UltraVista. With this large number of galaxies, we can then probe the evolution of the UV luminosity density, the cosmic star formation rate density, and as I say, the evolution seems to be quite smooth up to redshift 8 at least, and then there seems to be a decline. There is now, of course, not complete agreement between different studies of what happens beyond redshift 8, but surely with JWC we will be able to make progress also at this very highest redshift. However, all these great results so far that I showed are based on color selection for the photometric redshift. So we can probe the ensemble of galaxies, but first of all, we are never sure really that these galaxies are really at the very high redshift. So we need spectroscopic observations of at least a subset of the selected galaxies to validate the redshift, and therefore to validate the luminosity function, the mass function, the luminosity density, and their evolution. But I hope to convince you that spectroscopic observations are really needed for further aims and for probing really beyond just pure redshift and pure validation, because with spectroscopic observations, we can probe the ISM, we can probe the gas kinematics, we can probe the chemical enrichment and the IgM interaction, and last but not least, we can also probe the environment and how the environmental density impacts on galaxy evolution. These things can only be really studied with spectroscopy, optical and near-infrared spectroscopy. And indeed, in the last years, there have been many spectroscopic surveys that followed up this deep HST field, including, of course, the CANDELS field, but not only. And I have here a list of surveys, of spectroscopic surveys that actually focused on high-energy galaxies. This is probably not complete, is really only just to give you an impression of how much effort has been put in really following up all the many thousand galaxies we have with spectroscopy. So I like to mention, of course, WOODS, which was this VIMOS survey led by Olivier Lefebvre, and obtained optical spectra of 10,000 galaxies between redshift 2 and 6 in 3 different fields. And we also, of course, have 3D HST, which is a near-infrared survey. We have MOSDEP survey, which has recently been published in several very, very interesting articles and has obtained near-infrared spectroscopy of more than 1,500 galaxies. We have, of course, a great result from MUSE. MUSE has a tiny field of view, but can go really deep. And there's been many, many interesting works from MUSE. So in this context, a few years ago, we have designed and then carry out VANDELS, which is the latest and also last VIMOS ESO public spectroscopic survey. It's the last one because then VIMOS, after we finished the observations, was taken out and decommissioned from VLT. So in my talk, I will present VANDELS as a survey and also the main result, well, the first result, because of course VANDELS is still ongoing, and although we finished the observation a couple of years ago, the data reduction has only just been completed, and still we have not been able to work with the full data set, but already with partial data set, we obtained very, very interesting results. And so VANDELS consisted of about 900 hours of visitor time, visitor mode time, in which were spread over more than 250 nights in 3 years. So we finished observations about 2 years ago. VANDELS obtained spectra in the optical, so between 4,800 and 1 micron. And as I will show, the main features of VANDELS were that we obtained really ultra deep spectra of very high redshift galaxies. The raw data, because it's a public survey, the raw data become immediately public, but we also committed to reduce the data and provide them to the community. So every year we reduce a chunk of data. So currently data DR3 is available, and we hope to be able to release to the public the final the complete data set in about 2 months or within the end of the year. So the proposal focused on 2 key aspects, where first of all, we wanted to provide something of legacy value for the astronomical community. And most of all, we wanted to have different science from previous VIMOS survey, which were essentially redshift surveys. So we did not want to have another survey just to probe redshifts, but we really wanted to go deep and be able to determine physical parameters from our spectra. So for this reason, we had a relatively small, we focused on a relatively small area, so just 0.2 square degrees, but where we had already the best multi-wavelength data. photometric data, and we employed ultra-long integration. So our objects are observed for a minimum of 20 to a maximum of 80 hours per source. These are integration time which are unprecedented, because the deepest previous surveys was Woods, which only had about 10 to 15 hours integration. And we pre-selected our galaxies to be at very high redshift. So this is the sample, the sample in this histogram. In black, you have the VANDELS sample. So most of our galaxies are at redshift above 3. And we also had a small passive sample at redshift between 1 and 2. These are the targets which I just mentioned. So we had passive galaxies between redshift 1 and 2, and then we have star-forming galaxies between redshift 2.4 and 5.5. You see that the magnitude that we are reaching are not so faint, again, because we want to get really high signal-to-noise spectra. So we don't go extremely faint. We actually have, because I mean, it's not simple to really place slits in an instrument like that VIMOS. We also, of course, have another, say, sample of Lyman break galaxies, so star-forming galaxy, but fainter, where we go to age of 27 and redshift 7. So, of course, as I say, the aim is to combine then this optical spectroscopy with all the other data that we have, starting from the near-infrared grid spectroscopy, but most of all to all the photometry that is available for this field. So for the reasons, we chose the two main extragalactic fields that have the best data. So this is UDS, and this is the good south field. You can see here this is the VIMOS footprint. So VIMOS was made basically of 4 spectrograph, 4 MOS spectrograph, and this is the VANDELS observation. So our area covers a bit. The area we cover is double the area. The central area is covered by the CANDELS data. So this is where the deep HST data are available. But then we also have excellent multi-wavelength photometry for the area around. And each pointing basically is targeted 4 times, 20 hours for the bright targets, and then 80 hours for the faint targets. So this is the full sample we have observed in the end, and consists of more than 2,100 targets. And basically, these are how they are displayed in redshift mass and redshift formation rate space. So you see that we span 3 decks in stellar mass and 4 decks in star formation rate. So we're really sampling the star forming population quite well at redshift between 2.5 and 6, and also this sample of passive galaxies. So as I say, we will have spectra with very high signal to noise. So we want to do detailed studies of individual targets, but clearly there is many opportunities to explore also the properties of composite spectra, to explore the properties of galaxies by doing stacked properties in, for example, in bin of redshift, in bin of mass and redshift, mass and star formation rate, and so on, because we have so many objects, and so we can really make composite stacks with very, very high signals to noise. The data that is now available for everybody to use is the data release 3, which consists of 1,640 spectra, and of which 350 already available have 80 hours integration. So everybody can go and play with this data. I actually encourage people to go and get the data. This is the redshift distribution of the galaxies in the DR3 and the space distribution in 2 fields. And we also have our website as a database where we actually release more user-friendly data rather than they go into the ESO web pages. Of course, one thing that we were really worried before doing the survey was how accurate were our photometric redshifts. Of course, you don't want to spend 80 hours on a target just to find that your photometric redshift was wrong, because it would be a huge waste of time. And So luckily, we made a lot of effort to really have the best photometric redshift, not just for the CANDELS field, but also for the surrounding area. So many people worked on providing the best photometric redshift for selecting targets at the beginning of the survey. And actually it was a relief to see this plot where we plot the photometric redshift versus spectroscopic redshift. You see that really the number of outliers, so objects for which our photometric redshift was completely wrong, is really small. This is, in this plot, you have the entire set of 1,645 objects in DR3, and really you can count on one hand, maybe two hands, but it's really few for which the accuracy was not good. And this is very good. So, VANDELS provides plenty of spectra with high signal to noise, as I say, for detailed emissions and absorption line studies. So this is an example of an object that you can study with the VANDELS spectra. So you have, for example, Lyman alpha and carbon-3 emission, but of course a number of absorption lines. So in my talk, I will now present some results that have been obtained from partial VANDELS data sets. And of course, the credit doesn't go to me because there's many people that work on VANDELS, and this is some of the people that have actually worked on the data, and the results I will show are coming mostly from their effort. In particular, I want to present different things that provide examples of, on one hand, the advantage of combining 100 spectra to produce and analyze super deep stacks. So as I say, how you can study with stacked spectra the properties versus, for example, redshift or versus mass or star formation rate. Then I will provide examples of how it's a powerful thing to combine deep spectroscopy with multi-wavelength photometry, not such an easy as it can seem, but it's really powerful if we can combine things together. And then I will show some studies of how we can study the ISM with the best signal to noise spectra, and how we can study rare or faint line emitters, or in general, how we can also study emission line galaxies with the VANDELS dataset. So I will show with, I will start with a work that actually has been conducted by several groups also in collaboration, and which is the relation between the mass and the stellar metallicity, and also the UV slope in galaxies. This was actually one of the main drivers of VANDELS, so to derive the metallicity of galaxies from optical spectroscopy. And we know that metal and dust are really key products of stellar evolution, so they're fundamental to understand the star formation history of galaxies, for example. They also shape the spectral energy distribution of galaxies, and there is well known degeneracies of their effect also with age and with others. For example, we know that the UV slope beta, which is often used as a proxy for attenuation, depends also very much on metallicity, but we really want to know how this dependence is shaped. So in this work by Calabro et al., which has been submitted and I think will appear on arXiv as soon as we answer the referee, so probably in a few days, we use stellar absorption indices that are not sensitive to age and IMF to constrain the metallicity. So there's been several authors, and here I only list some of them, so Vidal Garcia, Marie, Valater, Rix, that proposed to measure the metallicity from stellar absorption indices. So there's been, I think in the literature, about 10, 12 indices that have been proposed. But some of them are, for example, contaminated by ISM absorption lines, and some of them are actually sensitive to IMF. So not all of them are really robust. So we did a lot of tests on mock spectra, and in the end, we found that there are two feeders, 1511 and 1719, which were previously proposed, that seem to be very robust. And so they're basically, they're equivalent to it, scales very well with stellar metallicity. And of course you need, because these features are really, really faint, you need, for this study, we actually decided to do, to measure them on stacks. So we actually decided that we need to measure with good accuracy, we need to produce stacks of spectra with a signal to noise of at least 30 in the continuum to beat the uncertainties. So we basically have a minimum of 30 galaxies per beam. And so in this work, what we did, so this is the sample that Antonello Calabrò used. Basically, it's a sample of 700 galaxies with a median redshift of 3.38. He stacked the galaxies in bins of mass. So here, concentrate for the moment on the black point. So he produced 5 stacks in bins of stellar mass, and then derived the metallicity. So actually, these are some of the stacks, where you can see again how faint the feeders we are talking about are. These are the other ISM absorption line, which of course are much more prominent. So the stellar feeders are really faint. And so first result that we obtain is that there is a clear mass metallicity relation in place at redshift 3. And it has a slope that is actually very consistent with the slope of what is found, for example, in the local universe by Zaidan collaboration for the Sloan galaxies. Because there is quite a lot of galaxies in our sample, we also try to split into low redshift and high redshift. And so here the high redshift sample is the red points. Now we can only do 3 beams in mass, but still the mass metallicity relation is quite well recovered, and low redshift is the blue points. So you see that there is a very marginal evidence for maybe some evolution of the relation between 2.5 and 3.5, but the two are really consistent with each other. So we find very, very marginal evidence for evolution. So we could actually say that there is almost no evolution between these two redshifts. Similarly, we also can construct a mass beta relation. And here again, these are actually all our galaxies in the points, and this is the median relation at the 2 redshift bins. And by combining the two, so again, we can derive the beta metallicity relation. And so actually in this plot, you see the points are the beta metallicity relation derived directly from the data. So stacking our sample, dividing our sample in 4 beams of beta slope, and then deriving the metallicity. And so we find this dotted line, which is the best fit relation. But we also actually, for consistency check, we also fit this relation first, the the mass metallicity relation. We fit this relation, the beta metallicity, and then from the 2 relations we derive this, and we obtain this blue, light blue curve, which is just a little bit steeper than the black one, but still consistent. Before going on, there was actually parallel to this, there was another effort to derive the metallicity from stacks in a completely independent form, from a global fitting of the stacks to Starburst 99 templates using Bayesian nested sampling. This was a work that came out last year by Cullen and collaborators, so also within the VANDELS collaboration. And this is a very different way, because instead of relying on some indices, in this work we actually did a fit to the entire spectrum, avoiding just the regions here in white, which are dominated by ISM or by emission lines. So we take out these regions because these are clearly dominated by ISM, and we fit the rest of the spectrum. And the results are luckily very similar to those we obtained in Calabrò. So the 2 methods obtain very similar results. This is the mass metallicity relation obtained by Cullen et al. And again, also no significant evolution observed in redshift. So in this case, we actually, in this work, we also compared the results to the hydrodynamical simulations, SIMBA, PHOEBE, and FIRE. These are 3 different sets of hydrodynamical simulations. And the result was that basically none of them really were consistent in terms of absolute abundances with what we found observationally, although the slope was quite well recovered by say almost all simulations. So here actually the results by Cullen et al. Are the gray points that you see. So the result by Calabro et al. Are the black points, and the result by Cullen et al. Are the gray points. There is quite a good agreement, even if the result by Calabro might be slightly above, so with a higher metallicity. And this might be due to the fact that maybe the two methods are sensitive to different elemental abundance, but they're very consistent within the errors. Interestingly, we also compare the result to prediction of semi-analytical models. So this is the comparison of the mass metallicity relation here to the left, and to the beta metallicity relation to the right. The yellow points are galaxies from the Gaia simulations, which actually use a light cone that has been actually made to mimic the VANDELS survey. And you can see that, again, this model reproduces the slope of the mass metallicity relation quite well, although there is an offset. The two are actually consistent at 1 sigma, but there is a consistent offset. And for the beta metallicity relation, the Gaia galaxies, again, have higher metallicity, apart from the redshift galaxies, which have a compared metallicity. Actually, just these Gaia models, this comparison between Gaia models and data was also put forward by Fontano et al. In a paper that is ready to be submitted, and they actually enlarged this comparison to study the evolution of the stellar mass versus stellar metallicity and versus gas metallicity relations from the local universe to redshift 3.5. So here to the left, you see the stellar metallicity versus mass relation at redshift 0, 0.7, 3.5. So this plot here contains the VANDELS data that I already showed in the previous slide, whereas of course these are lower redshift data from Zahid, and these are data from Galazzi et al. 2014. You can see that the Gaia models actually predict quite well the slope in all cases, but also the absolute value of the metallicity is well reproduced both at redshift 0 and 0.7, but not at redshift 3.5. For the gas metallicity, the model does a much better job because it reproduces quite well all data points at all redshifts. So Gaia is able to reproduce the observed evolution up to the highest redshift where data are available for what concerns the gas metallicity mass relation. And in this paper, actually, Fontano et al. Also studied the fundamental metallicity relation, so the mass transformation rate metallicity plane, and they show that is already in place at redshift 5, and again, with quite a good agreement with the data. Now that we have some very nice method to derive the metallicity, we have also applied to say other scientific issues, and here I provide 2 examples. So this is an application to find a possible relation between the Lyman alpha emission and the stellar metallicity. This is a paper, a very recent work by Cullen, and the motivation was that okay, Lyman alpha emitters, which we know are very interesting because they might be linked to Lyman continuum photon production, are thought to be low mass, relatively dust-free galaxies, and it's always say that they probably are low metallicity galaxies. So a link to low metallicity is expected, but has never been really demonstrated. Also because of I mean, it's not so easy to probe the metallicity of Lyman alpha emitters. They're in general very faint galaxies. So we went to look at the Lyman alpha emission in the VANDELS galaxies. So this time we took a sample of 760 galaxies at redshift above 3, where Lyman alpha enters the spectral range that is probed by our spectra. And we then measured Lyman alpha emission in our galaxies, and then we constructed 4 samples, dividing our sample in quartiles of Lyman alpha equivalent width. So we build a stack of the galaxies this at the bottom is the galaxy without Lyman alpha emission, and this at the top is the galaxies with the strongest Lyman alpha emissions, and these are the other quartiles. And then in this tax, we went to measure the metallicity. In this case, we applied the method derived by Coulomb et al. And here's the results. So from low to high Lyman alpha equivalent, we observe a decrease of a factor of 3 in metallicity. So it's the first time that we can really probe this link between the Lyman alpha and the metallicity. So Lyman alpha emitters are really low metallicity galaxies, or at least they are much lower metallicity compared to galaxies without Lyman alpha. Another thing we are going to do is to investigate the relation between the metallicity and the environment. This is something that Calabro is actually working at the moment. So we know that, as I mentioned already, environment is one of the ingredients that shapes galaxy evolution. And so the mass metallicity relation could be dependent also on environmental density, although results have not been conclusive so far. So we are making use of density maps that were derived for the 2 VANDELS fields by White et al. They were actually aiming at something completely different because they wanted to study how Lyman alpha emission actually depending on environment. But we're going to employ these maps, which were derived using photometric and spectroscopic redshift that are available in the field, not just VANDELS, of course, and to search for possible dependence on metallicity and environment. This work has just started, but I like to mention that this is also possible. Going back to Lyman alpha, there's a number of studies that you can do in VANDELS because we have so many galaxies showing Lyman alpha emission in our sample. And one nice example of what you can do is provided by this work by Og et al. Last year. And in this case, the motivation was to explore the possible slit losses effect when you observe Lyman alpha emission. So we know that Lyman alpha can be offset from the UV, from the continuum. And so in usual in slit spectroscopy, when you go and put your slit on a galaxy to determine if it's a Lyman alpha emitter or not, you might be missing your Lyman alpha emission. So there were some claims that the observed drop of Lyman alpha that you observe at redshift above 6, and that has been interpreted as a sign of reionization by many others, including myself, there were some claims that actually this could be due to the fact that as you go to higher redshift, Lyman alpha is actually more offset from the UV continuum, and you might simply be losing Lyman alpha because of a simple slit loss effect. So because in VANDELS we also have these 2D spectra, we could go and check whether there was actually this spatial variation. So the offset between the position of the Lyman alpha and the continuum were frequent, and what was the amount of offset. So in these 4 spectra, there are 2 examples in which the continuum is clearly offset from the Lyman alpha in terms of space. So here is the continuum and here's the Lyman alpha. The center is clearly offset. In this case, we can see the offset because the offset is along the slit. But of course, if the loss was outside the slit, we would not see the Lyman alpha. And in other cases, you have a Lyman alpha that is actually perfectly aligned with your continuum. Our result is actually that, well, first the spatial offset are quite small, of the order of a couple of kiloparsec at most, but most of all, it's reassuring to see that they are actually declining with redshift. So when we observe a declining Lyman alpha at redshift above 6 is actually because, probably not because of this spatial offset, because the spatial offset seems to be declining with redshift, but this is really because of the neutral hydrogen. So that's something reassuring. Nevertheless, the spatial offset are still something that one cannot ignore. For example, we make in this paper some prediction for slit losses for JWC near spec, multi-object spectroscopy at redshift 7. So because the slits in near spec are so small, even the small offset we see over the order of 1.5 kiloparsec at redshift 5.5 might cause great slit losses So in this plot here, we have, so we are assuming that the slit losses at redshift 7 are the same as those at redshift, so the offsets, sorry, at redshift 7 are the same as at redshift 5.5. And these are the slit losses one would get if when one observes with near spec. A bit better, of course, goes if the offset keep actually evolving and become even smaller at redshift 7, but still you see that the slit losses are quite important. So it's something that we really have to worry when we plan our near spec observations. Another very nice thing that we did with VANDELS was to look for rare line emission. So Lyman alpha is ubiquitous, but there are other line emission that we can see in the VANDELS spectra, for example, the carbon-3, but also the helium-2. The helium-2 emission is something very rare in galaxies, and it's also something very interesting that has been longer studied because standard stellar population cannot produce enough ionizing photons. So according to standard stellar population, unless you have an AGN, you cannot really have a lot of helium-2 emission. And so with standard stellar population, you cannot match the observed helium-2 strength, so that people have invoked population 3 galaxies as a possible explanation for the observed helium-2 emission in galaxies. Of course, now with the binary models, we have a better treatment of many things, and we do a better job at producing harder ionizing spectra, so more helium-2 flux. But still, it seems that this is not enough. So for this reason, we went to explore the helium-2 emitters in VANDELS, and this is the sample we got from DR3 data. So you see, we don't have many helium-2 emitters, even if our sample is very big, and even if we have many hours of integration, helium-2 is a rare rarity. So we have only about 25, 30 objects in VANDELS. So first thing, of course, we compare to stellar population models. As I say, now models like VPAS, which include binary stars, do a better job at reproducing the line ratio. This is, for example, a plot of carbon-3 over helium-2 versus oxygen-3 over helium-2. So our objects are quite well reproduced by the VPAS models. But if you consider just the equivalent width of helium-2, even for subsolar metallicity, none of the models reaches the high equivalent widths of helium-2 that you observe. So we have still too much helium-2 in these galaxies that even binary models cannot reproduce. So we need additional sources of helium-2 emission. As for the possible population 3 explanation, so population 3 should be metal-free stars. So we derive, we have applied the method derived by Cullen again to derive the metallicity of our helium-2 emitters. Of course, we cannot do them for these individually. These sources are typically quite faint, but we again can rely on stacks. So this below here is the stack of all our helium-2 emitters. And then we produce a matched sample. So these are the galaxies with the helium-2 emission, and we matched a sample of non-emitters, so with similar distribution of mass, star formation rate, and other physical parameters in order to have a really matched sample. And we measure in the stack the metallicity using this method derived that I showed earlier derived by Cullen et al. So both stack give a very low metallicity, 10% solar. But first of all, it's low, but not zero. So none of the two stacks is really extremely low metallicity. And the other thing is that the two stacks have identical metallicity. So our helium-2 emitters don't have lower metallicity compared to the similar sample of galaxy without helium-2 emission. So actually, this is consistent with the fact that we don't also see much difference in mass, star formation rate, and so on. So also POP3, it's not a good explanation. So again, we need to search alternative mechanisms to produce more helium-2 photons. And there are other mechanisms that have been proposed, for example, X-ray mass binaries or stellar stripping in binaries. And in this work by Saxena, we explore the possibility that X-ray binaries, or in any case some X-ray emission could be related to the presence of helium-2. We exploited the fact that in the CDFS field we have the Chandra 7 megasecond observation. Here I say kilosecond, is actually megasecond, and so we looked for X-ray emission from our helium-2 galaxies, and the result is that again there is no difference between the galaxies with helium-2 emission and no helium-2 emission in terms of X-ray in terms of X-ray flux. So again, we don't find any evidence for enhanced contribution of X-ray binaries, or in any case for a relation between X-ray emission and the presence of helium-2. So the only thing we can get is now get maybe some near-infrared spectra, or maybe with JWST to maybe assess the other parameters that could really tell us something more about the helium-2. So I think I don't have too much time left, but I want to still make a last example of what we can do with VANDELS. And this is particularly important because it involves the use of combining spectra and photometry. So when you do fit spectra and resolution fitting, and if you combine spectra and photometry, this is an example of one of our sources, a redshift 1.1. It's a passive source. Here you see the spectrum, and this is the multi-wavelength photometry. A known problem is that because spectra have so many points, you tend to say give too much importance to spectra and too much weight to the spectra. And so if you just simply fit the two together with simple minimization of chi-squared, you basically will come up with something that fits the spectrum very well, but maybe has some offset in the photometry. And this is an example here in the middle panel. So Adam Karnal actually applied bagpipes, which is this tool for to derive the physical parameters of galaxies. So he constructed within the bagpipe code sophisticated physical plus systematic uncertainty models that basically allows to treat the spectra together with the photometry, but in the spectra you allow for some basically calibration uncertainties. So there are some parameters that can allow for this extra calibration uncertainties. And in this case, you put everything together. So you do the systematic uncertainties and the physical parameters at the same time, and you get much better fit out of the data. So in this case, you see the full model has a chi-square that is 1, and so it's much better than the simple models where you don't have these extra parameters. So basically, with these complex physical models, you add some parameters that take into account the noise uncertainty for the spectra and the calibration uncertainty. In this particular work, the star formation history is described in this way, actually, because this is a work on passive galaxies. So actually, my point here was more really on the method of combining the spectra with the photometry. But still, I want to show this result because I think it's quite interesting. So in this case, it could relate the star formation histories to of the VANDELS passive source to derive with the time they quench. So in this plot here is the redshift of formation versus the mass, and he found that there's a very clear formation time versus stellar mass relation, which is observed in our data. And as I think I have one more minute, I also want to show this last result. This is something that is nice because it was something that we really didn't think of we could get with the VANDELS data when we actually wrote the proposal. So it's something that came really, say, as kind of a surprise. So in this work with Romain Thomas, we studied the intergalactic medium transmission using VANDELS galaxies. And so usually IGM transmission studies are done with quasars, with bright sources, with quasars. But in this study, we show that it is also possible to study the IGM transmission using galaxies because we have so many of them and because our spectra are so deep. So because the IgM transmission, of course, is degenerate with the dust content, what we did, we first used the multi-band photometry to estimate the dust content using true set fitting, object by object. And then we fix the EB minus blue, and then we fit the spectra at this fixed EB minus blue to determine the transmission of Lyman alpha. And this is our result as the transmission of Lyman alpha as a function of redshift in 4 redshift beams. The nice result is that our measurements are perfectly in agreement with the measurement for ESO from Becker et al., and also with the theoretical prescription. So this is something that came kind of unexpected because we didn't think we could do IgM studies also with the VANDELS galaxies. So I think my time is almost at the end. So in summary, I think I hope I convince you that these spectroscopic data are really an invaluable complement to deep multi-wavelength photometry to understand galaxy evolution. And that VANDELS provides really an excellent data set to study emission and absorption line galaxies, both individually and in stacks. So as I say, fully reduced VANDELS data, and by this I mean 1D, 2D spectra and noise spectra, plus of course at the right redshift are available. And most importantly, with the final data release that will hopefully be out before the end of the year, we will also provide enhanced data products for all our galaxies. So for example, we will provide physical parameters, the mass, the formation rate from the full spectrophotometric fitting. And also we will provide all the basic measurements for the emission and the absorption line, so fluxes, full width, maximum equivalent width, and so on. So I hope that people can find this data set useful for whatever study they can, also of course to as a nice addition to other sets of data that they might want to get. And so I encourage people to really go and check out our website and use our data for whatever they want. And I'm done. Thanks.
Thank you, Laura. So unfortunately we cannot upload, but so let's go now for the question. I stopped the recording.